20. What the hell is that? Okay, folks, this is Chapter 8, more trigonometry, and here we are getting into unit circle trig. Very exciting. What do circles have to do with these triangles? Let's find out. Again, I suspect that most people watching this will already know quite a bit of this, so we're going to move through this fairly quickly, beginning with degrees versus radians. Okay, so previously we've only been discussing degrees in this course. A circle can be divided into 360 degrees. Of course you knew that, but perhaps new to you is the idea that degrees can be further subdivided. 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. Certainly we already knew that 1 minute was equal to 60 seconds from time, but we can extend that idea into circles here as well. And we see that it has the same unit symbol as we use in time as well, with just 1 apostrophe for minutes and 2 apostrophes for seconds. As far as I can tell, minutes and seconds are not officially part of this course, but the conversion is easy to do by hand, and if you happen to want to do something on the calculator and you had some random decimal measure and you wanted to convert that to degrees, minutes, seconds, you're going to press this book icon right above the division sign. You're going to go to the second tab here, choose angle, which is the second option down, and then scroll way down. Don't choose this one. I'll show you what that does in a second, but then go convert to DMS for degrees, minutes, seconds, and then there you go. Now that one was kind of boring because that was an exact degree, because I'm an idiot. I got to put a decimal in there. There we go. So 23.45 degrees is equal to 23 degrees and 27 minutes. Okay, cool. If we wanted to go the other way around, well, we'd type this in, and then we could go right here and then convert to decimal degrees, and we get 469 over 20, which is, of course, equal to 23.45. How would we type this in, though? Where can we get this degree symbol and then this minute symbol from? Well, the easiest way that I know of is to press the pi button, and then there's a degree symbol, and then press it again, and then right there is a minute symbol. So there's your degrees, minutes, and then if you wanted seconds, you would just press the apostrophe again, and then go back and convert it to DD, stands for decimal degrees. I told you to skip the, let me delete this, I told you to skip the one up here that just said degrees, minutes, seconds. What that gives you is just a template that you can fill in, so you can just fill in the boxes. You can also get that template from pressing the button right next to the book and then choosing this one right here in the second row, second column. So that's all great, but hey, who cares, since minutes and seconds probably aren't on the exam anyway. And in fact, who the hell cares about degrees either? Radians are where it's at. So radians are the adult way to measure angles. No more of this kiddie nonsense with degrees. Okay, so we see the word radian is short for radial angle, and the idea, geometrically speaking, if we have a sector of a circle here where the length of the arc is exactly the same as the length of the radius, then the angle that we will have swept out to create this arc is exactly equal to 1 radian. Now we use this symbol C for radian, which is kind of weird. That's the official symbol that we see in the textbook. In practice, we don't write it. I don't remember seeing it ever on an IB exam, so don't worry about it. You definitely don't need to write down the symbol at all. And in fact, they say it's usually omitted. But here's the thing. When we write degrees, we always write the degree symbol. So if you write 2 pi, I assume you mean 2 pi radians. If you write 360, I assume that you mean 360 radians, unless you write a degree symbol up there. Okay, we got to be able to convert between these two units. This is what we need to know. To get from degrees to radians, we multiply by pi, divide by 180. To get from radians to degrees, we multiply by 180, we divide by pi. You should have The values in these two tables, they've got to either be memorized or you need to be able to calculate them really, really quickly. These are all simple ratios. They simplify nicely. You should be very comfortable going in either direction for these two tables.
Now this might surprise some of you because here I am, a math teacher, and yet I don't really like pi, at least not as an educational tool for you, the student, to learn about rotations around the unit circle. I mean, it's just not very intuitive. Why is it that one full rotation is equal to 2 pi? Why is half a rotation equal to 1 pi, and so on? It just doesn't make any sense to me. So I'm a fan of a new circle constant. It's called tau. It's really easy. 1 tau is equal to 2 pi. So now 1 full rotation, 1 tau. 8 rotations, 8 taus. The calculations are much simpler. I'll put a link in the video description to the Tau Manifesto. Lots of good reading there. There could be some mathematics or physics that's a bit beyond you at this exact moment in your life, but don't let that deter you. Give it a read. I'll also put a link to a video debate hosted by Numberphile a couple of years back. Personally, I think that the mathematical establishment rigged that one in favor of pi, but I mean, what can you expect? You know, the world is never working on the side of the true revolutionaries. It's true, you won't see tau anyway in a textbook anytime soon because it is new and change takes time. But I think that the IB should accept it if you use it on an exam. I certainly will. But the IB has stated that they'll accept any sort of mathematically correct notation. So square brackets, round brackets, for example. You can use decimal points or commas. They'll figure out what you mean. So I think you should give it a go. Hey, look. I just walked half a tau around that pond.
This is a good time to point out on the calculator. You can tell what mode you're in just by looking at the top right-hand corner of the screen. So I'm currently in Radian mode, which means that if I were to type in the sign, for example, of 30, I'm going to get a weird-looking answer because it's interpreting that as 30 radians. On your handheld device, you should have the most updated operating system. I currently don't have the most updated operating system on my computer for some dumb reason, but on your handheld, you should just be able to scroll the mouse right up here where it says RAD, click it once, and through the magic of jump cuts, it will change into degree mode. And now, when I type that same thing in, I get the 1/2 that I was expecting. The exact same functionality will occur when we get into graphing. All you'll have to do is click up there on your graph screen, and then you can change rapidly between degrees and radians. Section B is our reminder about arc length and area of a sector. Now, I said in that original video that the formulas were way nicer once we have radians, and that's true because we know from our conversion on the previous page that 2 pi radians is equal to 360 degrees. So those two terms can just cancel out if we're thinking in radians, leaving us with arc length is equal to theta times the radius. And then likewise, pi radians is equal to 180 degrees, so that's going to simplify down to just 1/2, and so we have an area of a sector of 1/2 theta r squared. And these, by the way, are the formulas that we have in the data booklet at the bottom of page 6, SL 3.4. They give us the formulas in radians. Okay, section C, we're into the unit circle now. It's just a circle with a radius of 1. And we're going to be imagining a point moving around that circle. We'll call it point P. If that point moves in a counterclockwise direction, then we consider the angle to be positive. Counterclockwise, or depending on where you're living in the world, perhaps you say anticlockwise. If that point moves clockwise around the circle, then the angle will be negative. We can now define our sine and cosine functions in terms of that point P as it moves around the circle. We still have a right triangle here when we're in the first quadrant, but notice now that the cosine of this angle must be equal to A divided by 1. 1 is certainly the hypotenuse given that we're on a unit circle. But A is simply the x-coordinate of our point. Likewise, the sine of theta is b divided by 1, where b is the y-coordinate of our point. And so this will hold true no matter where point P is. Cosine of theta is the x-coordinate of point P. Sine of theta is the y-coordinate of point P. That's true when we're in the first quadrant and we have an obvious right triangle. It's also true when we're in any other quadrant. From this, we can deduce that both sine and cosine must be in between -1 and +1, as the x-coordinate and the y-coordinate of that point vary in between -1 and +1. They can never be outside of those boundaries. We can similarly think about the tangent function. If you wish to look at the geometrical argument here, please pause and take it in. You'll also see why the tangent function has the name that it does, in that it shares its name with the tangent line of the circle. That is not a coincidence. They are geometrically related, as we see here. But again, what do we really need to know about tangent? We saw it previously. It's equal to sine divided by cosine. We can also say that the tangent of theta is therefore the gradient, or the slope, of the line going from the origin, O, to point P. Since the sine of theta is the y value and the cosine of theta is the x value, we see that that does give us a change in y over the change of x. All right, moving forward now, we want to start thinking more about the 4 quadrants of the xy plane. So they go in counterclockwise order, starting in the top right. And what we need to know is that all 3 of these trig functions have positive values in the first quadrant. Sine is the only one with positive values in the second. Tangent is the only with positive values in the third. And cosine is the only with positive values in the fourth. And this should make sense, again, if you consider sine and cosine and tangent in terms of the x and y coordinates. In the second quadrant, we have a negative x value but a positive y value. So that should be a negative cosine but a positive sine, and so on. And there's lots of ridiculous things you can use to try to memorize this. The book suggests all silly turtles crawl. Whatever, I don't know. When I was in school, we had like all students take calculus or something like that. I don't come up with your own. I don't care. All right, but notice that we're talking here about quadrants. We're not talking about angles. We're not saying just all 3 of the trig functions are positive when the angle is between 0 radians and pi over 2 radians. We're saying the first quadrant, and these arrows continue forever to go around, right? So we can have angles that are bigger than 360 degrees, bigger than 2 pi radians, and we could also have angles that are negative, so that could be like -45 degrees, negative pi over 4 radians. And these angles can be as large as we want them to be in the positive or negative directions. But when our angle ends up in one of those 4 quadrants, we know whether the sine, cosine, and tangent functions are positive or negative. And this brings us into the idea of periodicity, right? So sine and cosine values and tangent values, they repeat as we go around the circle. It doesn't matter how many times we go around the unit circle. If we end up in this particular location, whether I rotated just that much or 2 pi radians and then that much extra, I'm in the same exact coordinate, so the cosine and the sine and the tangent values should be exactly the same. And so we get this identity here, which says that the cosine of any particular angle has to be equal to the cosine of that angle plus 2k pi. So we have 2 pi, which is a full rotation, and then we have k, which is an integer. So we're either rotating around none of these, or 1. 2 pi is 1 full rotation. 2 full rotations would be 2 times 2 pi, and so on. And we're going to get the exact same value as if we had just done no additional rotations. And same idea here with sine. Sine of theta is equal to sine of theta plus 2k pi. Tangent, on the other hand, it actually ends up repeating a little bit more often. We don't need to add 2 pi, we can just add 1 pi each time. So tangent of theta is the same as tangent of theta plus k times pi. This is all easily verifiable through compound angle formulas, which we'll get to later on, not in this video, but later on in the course. It's also easy to verify these by thinking in terms of function transformations, which we will get to later on in the course. And that's actually what I would recommend that you do once we get up to it, but I'm a visual learner more than I am an algebraic type of guy, so I never really like to memorize these formulas. I can just make sense of the pictures by thinking about them, and then I can derive these formulas if and when I need them. And here's a few others, by the way, and they're given both in degrees and radians. I want to make one edit, though. I'm not sure why the book decided to list these only as though they're 1 pi or 2 pi. We can consider the bottom two is similar to the page previously, so that's 2 pi times any integer value. So that could give us 2 pi or 4 pi or 6 pi, etc. Those are all going to be the same. And then the two on top, we need to have specifically an odd multiple of pi. So we could have 1 pi, and we'll get that down here if k is equal to 0. If k is equal to 1, then we'll get 3 pi. If k is equal to 2, then we'll get 5 pi, and so on. So for the top two, we need odd multiples of pi, and those will all be, well, those identities will all stand. And you could do something similar with the degrees on the left, but I am not a child, so I don't want to think in terms of degrees. And on that note, section D is really just about memorizing the sine and cosine values of various angles in radians. So you might want to just commit to memory an image like this. So this is our unit circle with the important angles listed in both degrees and radians. And then we have coordinates, which of course we know give us the cosine value and the sine value for each of those points. Really all you need to memorize is what's in the first quadrant, and then think in terms of geometric like reflections. So this point has an x coordinate of 1/2, a y coordinate of √3/2. That point's going to have just the same coordinates, but the x value is going to be negative. And you can think about that. This is, okay, degrees is easier, right? So that's 60 degrees from the horizontal. Well, 120 is also 60 degrees away from that horizontal. And so that's how I like to think of it. That shows me the reflections. I'll show you another one down at the bottom. Let's do this one here. 5 pi over 4, or 225 degrees. Well, from the horizontal, that's up 45 degrees. So I know 45 degrees is the important one. So I think in terms of the first quadrant, 45 degrees, √2/2, √2/2. But obviously in the third quadrant, both of the coordinates would have to be negative, so I would just change them both to negative. And that's how I like to do this. I have all of these memorized, and then the rest is just reflections. As another option for you, I won't go into it here, but you can certainly Google trigonometric hand trick, and there'll be a ton of websites and videos that will explain to you, you imagine, kind of like this picture's got going on here. Your thumb is a y-axis, your pinky is an x-axis, and then you can work out what the other trig ratios are from there. But again, you look that up on your own if that's the way you want to go. Section E is just about this one single trigonometric identity, which you can find near the top of page 7 in your data booklet, SL 3.6. It is called the Pythagorean identity, and it comes from, obvious connection to the Pythagorean theorem here. Again, we're talking about a right triangle with a hypotenuse of 1. And that gives us the fact that for any angle, if we square the cosine value, square the sine value, add them together, we get 1. This is super duper helpful. So I just want to show you a few examples of it here. First, if we wanted to find possible exact values of cosine of theta, how can we do that? One way, and the way the book's going to show us, is using this identity. It's real easy, right? We're going to do cosine squared plus 2/3 squared is equal to 1, and then we're just going to solve for cosine of theta. We notice that we have cosine theta squared here, so this is kind of like a quadratic. So we need to take the square root, and we'll keep both the plus and the minus as our two answers. And visually, we see that there are two possible places for our point P to be, and likewise two possible angles. We could have either that one, or we could have that one. But another way to look at it is if you've got a right triangle and you know that the sine is 2/3, let's call that theta. That means we've got an opposite of 2, and a hypotenuse of 3. From there, we can deduce with the Pythagorean theorem that the adjacent side needs to be the square root of 5, and therefore the cosine of that angle will be the square root of 5 over 3. And then we just have to remember, hey, it could be positive or negative, so keep both answers. Some problems are a little bit more exciting. So here we're told the tangent value is -2. We also are told that theta is in the 4th quadrant. So that means that sine's going to be negative and cosine's going to be positive. Okay, give exact answers. This one's kind of cute for how we're going to figure out from tangent what sine and cosine are. So we use the fact that tangent is sine over cosine. And then we're just going to work with here. We're going to multiply cosine on both sides, giving us that. And then we can use our Pythagorean identity from there, just substituting in the -2 cosine in for sine. And now we have a quadratic equation in terms of just cosines. So we do some basic algebra, blah, 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 blah. Okay. And then we get cosine is taking square roots, just plus or minus 1 over root 5. But of course, we've already established that cosine had to be positive. So we'll keep just the positive value. And then from there, we could work out what sine is any number of ways. I guess the easiest one is just to use that, since we know that, right? We're just going to take this value and multiply it by 2, or by -2. But you could also, I guess, build it from a right triangle again, or substitute back into here. But those would be dumb ways. That's working way too hard. And now, section F, combining these ideas with that of inverse trigonometry from the last chapter. We're going to find angles. We're going to look at 2 examples here. This is one example with 3 parts. Here, each of the trig values are positive, and that actually makes it pretty easy. I'm just going to show it all to you here at once. If we know what the trig value is, we use inverse trigonometry on the calculator to figure out what our answer is, and then we remember that there could be 2 possible answers in between 0 and 360, so we give them both. Okay, nothing really interesting here. However, had those trigonometric values been negative, we're going to have to think a little bit harder. Okay, no, the last one was in degrees, this one's in radians. No matter. Show it to you all again here. So when we get our answers now, the calculator is going to give us, in the case of inverse sine and tangent, it's going to give us a negative angle. And in the case of cosine, it's going to give us specifically the obtuse angle out of the possible ones. And we can understand why this is later on when we've really formally studied the inverse trigonometric functions. But for right now, just think about the problem when you're doing it, check back with what possible answers they want, and just whatever answers you get, force them to fit within the domain that's given, and you'll be fine. Last section here, G, is just about straight lines, but thinking in terms of trigonometry. So if we've got a line, the gradient of that line is equal to the tangent of the angle that that line makes with the x-axis. And there's some really simple geometric proofs, so I include them here in case you want to take a look at them. But other than that, this is really easy stuff. So here's two examples that I think are very straightforward. And today's video quotation answers the question, why do I include quotations at the end of my videos? And it is from popular mathematics and popular science writer Martin Gardner, who said, biographical history as taught in our public schools and also our private ones, if I may interject, is still largely a history of boneheads, ridiculous kings and queens, paranoid political leaders, compulsive voyagers, ignorant generals, the flotsam and jetsam of historical currents. The men and women, I may interject again, who radically altered history, the great scientists and mathematicians, are seldom mentioned, if at all. And I aim to change that.